The Merman version of the Bell theorem works like this, and it requires no quantum mechanics. It's simply a result, and these results can be used to rule out the possibility that the particles have some kind of localized structure, that one doesn't depend on the other, such that you could figure out what those properties are all by itself without reference to anything else. Here's the idea of the setup. You have a machine in the middle that sends particles out with a button on it. And when you press it, a particle goes to the left and a particle goes to the right. And then you have two detectors. And the detectors have an indicator that you set to either 1, 2, or 3 on one side and 1, 2, or 3 on the other. You can set any combination of those, 1, 1, 2, 2, 3, 3, or 1, 2, 2, 3, 1, 3, 3, 1, and so on. When you press the button and a particle goes to each detector, one and only one light will light up on each of these receivers. Either the red light will light up on one of the receivers or the green light will light up. So you get a red light or a green light on the left and a red light or green light on the right, but you never get a failure to light on one side or the other, and you never get both lights lighting up on one side or the other. In other words, for each run of the experiment, each press of the button, particle going each to one of the detectors, you could summarize the results as being the place that the pointer is, 1, 2, or 3. So you could summarize that by saying 1, 2 would mean 1 on the left, 2 on the right, and what the lights do. So if the left light lights up red and the right light lights up green, you could summarize a particular run of the experiment as being, say, 1, 2, red, green. Okay? That's what we do. When we do this run over and over again, we could set the detectors to 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, or 3, 3. And we just press the button and see what we get. And then we write down what it is. 1, 1, red, red, 2, 2, green, green, etc., corresponding to the runs of the experiment. This experiment will have a certain set of results, and we'll talk about them. There'll be a result A and a result B, and we'll see that the combination of these results rules out the possibility that the particle contains all the information needed to tell you whether the red light will go or the green light will go, depending only on that receiver's position, 1, 2, or 3. We will rule out the localized explanation. That's the goal of this experiment. At the 1927 Solvay conference, Einstein kept coming up with thought experiments that he thought could show that you could have a definite value of both position and momentum, and that quantum mechanics was unable to capture those two variables simultaneously, and therefore that quantum mechanics was incomplete. That's what Einstein was really bothered by. He was not trying to say quantum mechanics was false or gave wrong predictions, but that you could actually show that there was a definite momentum and position at the same time, and that quantum mechanics simply failed to capture that. It was a question of our ignorance, or the ignorance afforded by quantum mechanics, not of a fundamental incompatibility between having a simultaneous value of position and momentum. So Einstein said, imagine that we have the two-slit experiment and we send particles through. Well, he said, by measuring the amount of momentum kick that the electron gives as it passes through one slit or the other, we could determine exactly whether it was going through one or the other and outwit this idea that somehow it went through both. We could actually just detect it. Well, Bohr said, look, suppose you have a slit in a little window on a weak spring. So we actually can measure the momentum kick that the electron gives this window as it goes through. Well, how would that work, Bohr says? It would work by measuring the position of the window before the electron went through, and then seeing what happened to the window, its response to the kick it got by the electron. But let's reason carefully, says Bohr. If that window on the suspended window has its position measured precisely by an indicator on the side of the frame, then the window itself has a superposition of all different momenta, because the position of the window and the momentum of the window obey the uncertainty principle. But if the window has a combination of all the different momenta that it could have, forced that way by being at a definite position, then it's going to give the electron an unknown kick when it goes through. The electron's not just going to hit a stationary window. The window is itself going to be in a combination of different momenta. Well, getting a kick of all these different momenta means that the electron's going to have all different wavelengths. And so it won't exhibit the kind of nice interference pattern on the photographic plate that we expect. In other words, by measuring the process of the electron going through that window, we make it act like a particle and not like a wave. So, Bohr says to Einstein, your idea doesn't show that the particle can be both a particle and a wave. If we measure its particle-like aspect by looking at the kick it gives, by trying to fix the window, then we're going to throw the electron into a combination of all different momenta, and it will no longer interfere. Bohr says, the world is safe for quantum mechanics. You have not shown that there's a reality it's failing to capture. Einstein, after many of these exchanges with Bohr, never stopped thinking about ways to show that there was an underlying reality that quantum mechanics didn't capture. He was bowed, not defeated. At the next Solvay meeting in 1930s, the sixth Solvay meeting, he came up with an imaginary experiment that you might be able to picture building that worked like this. Suppose you had a box, and the box had a clock in it. It was suspended by springs, so you could weigh the box before and after it launched a photon. Well, by determining the change of weight of the box, you could figure out the energy of the emitted photon. And there was a clock in the box, Einstein said. By using the clock, you could determine when the photon left, so you know both its energy and its time of release. Well, says Einstein, quantum mechanics says you can't have a simultaneous measurement of energy and time, just the way you can't have position and momentum. So what do you say to that, Bohr? Your theory says I can't have both, and I've just designed a device that gives me an answer. I, Einstein, have shown a device that shows you exactly how to get a value for the energy of the photon and a value for the time at which it's emitted. Bohr was really troubled by this. He did not know how to get around it. He took long walks. He thought, oh my God, this is the end of quantum mechanics. Einstein's really gotten around the uncertainty principle this time. It really is incomplete. And then Bohr realized the error of Einstein's ways. If you take that box and you weigh it before the photon is emitted, then we have to see that it's at a certain height, suspended by the springs. But as soon as I get a certain height to it, I know that it has an uncertainty, a combination of all the different momenta up and down. And the more finely I measure the height of the box, the weight of the box before it launches its photon, the bigger the spread of momenta. So when we measure it initially, it's going to take a long time for it to settle down if I make a very fine measurement of its weight before the emission of the photon. But Bohr says, look here, Einstein, you taught us that the height of the box in a gravitational field is going to determine the rate that the clock is running. So if there's uncertainty in height that corresponds to all the different combination of momenta that it's going to have, then there's going to be an uncertainty in the clock rate and therefore an uncertainty of the time at which the photon was emitted. So, says Bohr to Einstein, you're hoisted on your own relativistic petard. Your idea about the relativity of time in a gravitational field actually shows that there isn't a simultaneous value of the time of emission of the photon and the energy of the photon by weighing before and after the little box. In this way, back and forth in these exchanges that went on over a long time, by 1930, Einstein thought he could come up with a response to show that there really was something incomplete about quantum mechanics, and Bohr so far was able to defeat each of Einstein's propositions. And yet Einstein's desire to show that quantum mechanics was correct but incomplete never stopped. Between 1930 and 1935, he struggled to find a counterexample. And in 1935, he hit back with one of his most famous counterexamples, which we'll discuss next time. Einstein's fight against quantum incompleteness was ultimately a losing one, as we will see. But it shows the tremendous attachment that he had to a picture of nature in which we could have a reality outside of us, a mind-independent, localized reality that would tell us how the world worked and that we could get as close to it as our measuring devices and calculation allowed. Einstein never gave up his hope that quantum mechanics would be proven to be correct, but incomplete. The strangeness of quantum reality is still sinking in almost a century after the theory came into existence. And that's testimony to how radical it was. If relativity, in a sense, disrupted the culture more deeply at a philosophical, artistic, architectural level, we don't really have a lot of quantum architecture, but there was an attempt to have a relativistic one. It's perhaps because Einstein's theory came first. And in its newness, in its ability to serve as a kind of icon and avatar of modernity, it had an impact that went deep into the culture and in fact helped form the possibilities for the quantum theoreticians to criticize such basic ideas as causality, completeness, reality, and even the very notion of the world, which we'll come to in a moment. This idea that we've been discussing of the entanglement of particles that begin entangled and stay entangled even when they're far separated in space is very disturbing. One physicist, Stapp, put it this way much more recently. Scientists of the late 20s, led by Bohr and Heisenberg, proposed a conception of nature radically different from that of their predecessors. Their theoretical structure did not extend down and anchor itself on fundamental microscopic space-time realities. Instead, it turned back and anchored itself in the concrete sense realities that form the basis of social life. This radical concept was called the Copenhagen interpretation. This idea that Bohr constantly came back to, that we have to ground our concepts in things that we experience, that we can't imagine ourselves outside of the possibility of measurement, was fundamental to this new theory. Objects were entangled, and when we measure things, we have an effect on the world. We prepare the world in a certain way that alters reality. There is no independent reality that simply exists that we can approximate in different ways. What Bohr said, his followers advocated, was that when we measure things, we only see pure states. We either see a dead cat or a live cat. We never see a superposition of dead plus live. We see an electron in one place and not another. If you take a photographic plate and you see where the electron arrives, it arrives in one spot. It's not a cloud of mist. It hits in one place rather than another. When we measure momentum, we get a momentum, a particular value of momentum. We don't get a fog. But normal quantum mechanics always develops these superpositions, combinations of states, an electron traveling through two slits, for example. So how are these reconciled? Well, in the Copenhagen interpretation, one of the fundamental assumptions, the beginning point, is that you calculate all the different ways that a physical process can develop, and they each contribute something to the state of the physical system. But when you measure, we get one and only one value of a particular thing. And the question then arises, what is it about measurement, when we conduct a measurement, that's utterly unique in physics? There's no way, for instance, that all on its own, that a physical system will suddenly go into this pure state when it's been a combination of states before that. This is really strange and very disturbing to physicists. Many physicists hate the idea that there's something special about us, about the measurement act. or at least they want to explain what it is about the Measurement Act that's relevant to this sudden collapse of the superposition into one state, the sudden collapse of dead plus live cat into dead cat, or into live cat. Well, you might think that this was simply a matter of little things and big things, that electrons might be in a combination of states, but big things wouldn't be. That's what Schrödinger was showing would not happen, that you could extend the quantum process from an atomic decay to a Geiger counter to a bottle of cyanic acid that then would kill the cat and make the whole thing into a quantum system. So bigness was no guarantee that you could be exempt from the combination of states. And Schrödinger took that to be an argument against quantum mechanics, or at least for its incompleteness. So the question arises, if quantum systems, by their nature, are constantly in superpositions, say, of a Geiger counter going off or not going off, then why, when we actually look to see where the electron arrives or what momentum it has, we always see a value? We don't see the electron arriving at many different places. We see the electron arriving here. And statistically, when we add all the different hits on the photographic plate up, we see a wave-like distribution of an interference pattern of their arrival points. But any given electron, when it hits the paper, and we say, where is it? It's in a particular place. So you might think that this collapse of a combination into a single state was just because big things don't behave quantum mechanically. But that's just what Schrödinger said was not true, that you could rig up a quantum system to be attached to something big like a cat, and then the cat should be in a combination of dead plus live. And that, for Schrödinger, was an argument against the very possibility of having this description of physics and measurement. Other physicists tried desperately to figure out what it was that made the wave packet collapse from a combination of different states into one state. Eugene Wigner, for example, had the view that it's consciousness that suddenly reduced this combination of states into one, dead plus live into just dead, or dead plus live into just live. Now, that really bothered other physicists. And in fact, it's rather surprising that Wigner, this sort of hard-boiled, group theoretical, very technical physicist, someone who was trained in engineering as well as quantum theory, was willing to resort to consciousness. What was it about something as evanescent as consciousness that could cause the wave packet to collapse into a pure state? Other people, like the physicist John Wheeler, who was involved with early work on nuclear fission, said that it's actually making a recording of a measurement that caused the wave packet to collapse from a combination into a single state. Other people, like the philosopher Hilary Putnam, philosopher Kripke, argue that it's actually logic itself that needs to be altered to account for the quantum world. But it may be that the strangest interpretation of all, but one that goes deep in the heart of theoretical physics, was invented by Everett in 1957. And it's called the many worlds interpretation. As strange as this interpretation is, it's actually subscribed to by a very large fraction of contemporary physicists and has analogs in the multiverse that we'll talk a little bit about at the end of the course. And the idea is this, that when quantum mechanics has a measurement, when more than one possibility is conceivable, dead cat, live cat, particle going through A, particle going through B, Geiger counter firing or not firing, that actually every aspect of quantum physics outcomes occurs, but that at the moment when a multiplicity of outcomes is available, they all actually happen, each one in a different world. And these worlds are not attached to each other in any causal way. So there's a world where the cat dies and a world where the cat lives, and they separate. And we happen to find ourselves in one or the other. We might find ourselves in the world where we open it and see a dead cat, we might open it up and see a live cat. This is really strange. And to understand why physicists have been willing to subscribe to something as ontologically profligate as this, to this multiplication of the universe in this way, you have to understand how disturbing it was that there was something that people did that suddenly collapsed the underlying physics from a multiplicity of states into one. That they wanted the physics to just function. And the physics that said, the equations that said there were these different outcomes, live cat and dead cat, would just continue. That the measurement wouldn't collapse this multiplicity into a single thing, that they would all actually happen. And that the probability, if, say, you had a specific kind of setup where 9/10 of the time the cat lived and 1/10 of the time the cat died, that would mean 9 copies of the live cat worlds would exist and 1 copy of the dead cat world. And the fact that most of the time we find ourselves in the live cat world would just reflect the fact that there are more of those worlds than the other. All of these interpretations, consciousness, measuring devices, many worlds interpretation, reflects the desperation, the desperate metaphysics, the incredibly unexpected nature of the quantum world. So where are we at the end of this set of reasoning? We've seen that relativity was implicated in the whole history of modernisms and the intersection of philosophy, technology, and physics. We saw how relativity was associated with the annihilation of the idea of the absolute, the reformation of time, space, and simultaneity. We saw in general relativity how the very idea of force was gone. We saw how intuitions about what our native ability to live in a Euclidean world was actually challenged, and non-Euclidean geometry became not an option, but actually a necessity to proceed with physics as Einstein developed it in general relativity. We start to think about the physics of the world as a whole, the universe as a whole, to think of cosmology as something that could be addressed scientifically. In quantum mechanics, building on these radical changes in the world that accompanied relativity, we saw even more disturbance in our expectations. The disturbance of causality, determinism, visualizability, of Einstein's hopes and fears for physics, the hope for causality, the fear of incompleteness. We are left from quantum mechanics with an entangled universe, one that, as we'll see next time, is not just a matter of philosophical interpretation. These entangled particles get associated with some of the most exciting technological developments that you can imagine. Quantum cryptography, the idea, for instance, of quantum computation, which could radically reformulate how computers work in generations to come. Quantum mechanics seems to keep being fruitful, generation after generation, as it opens up a world as productive as it is philosophically disturbing.